All right, folks, welcome. A video today on orthogonality. In this video, we'll talk about the basics of orthogonality. We'll talk about how orthogonality can be defined by what's called an inner product. For many cases, an inner product for us is going to be the same as our familiar dot product that you may have seen elsewhere. We'll talk about the idea of the norm of a vector, and then we'll finally talk about what makes vectors orthogonal. It turns out that all sets containing vectors that are mutually orthogonal are also linearly independent. That's a pretty special feature. So we'll see how to cook up an orthogonal set from a linearly independent set from the Gram-Schmidt process. Okay, a quick reminder about complex arithmetic. If we have a vector that has elements from the complex field, U is an element of Cm, we can define the conjugate of that vector over bar U. The conjugate of the vector is in each element is the conjugate of that element. Okay, so it's just a quick reminder on how to conjugate complex numbers. All we do is change the sign of the imaginary part of that number. So if we have a complex number a plus bi, its complex conjugate is a minus bi. Okay, one useful thing is that the complex conjugate of a real number is always itself. That's a quick way to tell whether a number is real. So if you take the complex conjugate of a number and get back the same number, then that number is a real number. And that goes for vectors too, again, because complex conjugation is component-wise with a vector. Okay, so this first theorem is a theorem that you can prove just by using the properties of vector addition, vector equality, and complex conjugation. This theorem says that the conjugate of a sum is the sum of the conjugates. Here's another theorem that you can prove using properties of complex conjugation, scalar multiplication, and vector equality. This theorem says that the complex conjugate of a scalar multiple is the scalar multiple of the complex conjugates. Okay, so somehow complex conjugation works how we'd expect it to. You can do it before or after taking a vector sum or a scalar multiple and get the same answer. Okay, let's talk about inner products. Here's the definition of an inner product. It might be a little different than you've seen before, so just be ready for that. If U and V are vectors with possibly complex elements, then the inner product of U and V is the conjugate of U1 times V1 plus the conjugate of U2 times V2. And we keep summing all the way out to the conjugate of the last one, UM times VM. Okay, so again here, the computation is conjugate the first vector, leave the second vector alone, and then sum the product of their elements. Okay, I want to point out a little notation alert here. We've seen these angle brackets before. Angle bracket S, where S is a set of vectors, is the span of that set of vectors, right? All possible linear combinations. Similarly, if we have explicitly the vectors, say U and V, then angle bracket set of vectors UV is the span of those vectors UV. Okay, so here our notation for the inner product is a little bit different, right? Inner product UV doesn't have any squirrely brackets or a set of vectors. Okay, so angle bracket UV denotes the inner product of UV. So again, what you do here is conjugate the first, leave the second alone, and sum the products of the elements. Okay, so here's an example of an inner product. Let's go ahead and have a look at the inner product of U and V for U equals 2 plus 3i, 5 plus 2i, and negative 3 plus I, and V equals 1 plus 2i, minus 4 plus 5i, and 5i. Okay, so again, we'll conjugate the first, leave the second alone, take the product of those elements and sum them. And when you do that, here's what you get. You get something like this, right? So again, the conjugate of the first vector, leave the second alone, sum the product of each element. Okay, so here you can see I've got a small typo. This should be a minus instead of a plus. In any case, the rest looks okay. 2 minus 3i times 1 plus 2i, 5 minus 2i times negative 4 plus 5i, negative 3 minus I times 5i. And when you do the complex arithmetic and write it all down here, it turns out that what you get is 3 plus 19i. Okay, so again, here is a scalar quantity. That scalar quantity, possibly a complex number itself. Let's go ahead and do another example. Here's an example involving vectors that have all real elements. Okay, so again here, in the case where all of our vectors have real elements, it turns out that the inner product is our standard dot product. Okay, so I'll let you work this out on the worksheet, but what you should get is that the inner product, or in this case, the dot product of W with X is negative 8. A couple of theorems involving linearity and distributive properties of inner products. The first says that the inner product of a sum with another vector is the sum of the individual inner products. And that, as it turns out, is true whether the sum is in the first or the second position of the inner product. Okay, and again, the way that you work this out is by using the definition of the inner product and then properties of vector addition, scalar multiplication, and elements of the complex field. So I'll go ahead and illustrate this for the first one. Okay, so we see that the inner product of a vector with another vector is the sum I equals 1 to n, where you take the product of the conjugate of the first element with the second element. Okay, so we know that when it comes to vectors and their components, that the conjugate of a sum is the sum of the conjugates. And then we know we can distribute that sum over the sum. The sum of the sum is the sum of the sum. Now, of course, the first sum we see is exactly the inner product of U with W, and the second sum we see is exactly the inner product of V with W. So we see that the inner product of a sum times a vector is the sum of the individual vector's inner product with the second. Okay, and sort of a similar thing works out when we have scalar multiplication too, right? And the only item is here that you have to be a little bit careful with complex conjugation because we always conjugate the first vector and leave the second vector alone. So as it turns out, when you do that, our scalar multiple comes out as a conjugate if it's attached to the first vector, and it comes out as itself when it's attached to the second vector. So I'll ask you just to read those and check those out and let me know if you have any questions. Similarly, and this is sort of related to the last one, the inner product is sort of our first operation that we see as not commutative. So if you would like, you could think of the inner product as a new way to multiply vectors. Okay, and usually when we're talking about numbers, right, for instance, 5 times 7 is the same as 7 times 5. But here we see that the inner product of U with V is the same as the complex conjugate of the inner product of V with U. And the way that this works is by thinking about the definition of the inner product, and then again by thinking about what complex conjugation does to the first and second elements respectively. So again, the inner product of U with V is the inner product of V with U with a complex conjugate. Now, I'll point out here that when U and V are real valued vectors, that complex conjugation yields another real valued vector, so that it turns out, and I won't go through the proof, the inner product of W with X is the same as the inner product of X with W. Okay, let's go ahead and talk about the norm. The norm of a vector is a way to measure length. And for any real or complex valued vector, it's denoted by the square root of the sum of what's called the modulus of each element squared. Okay, so let's talk about this idea of modulus a little bit. In this case, again, the notation that looks like these absolute value bars of the ith element of u squared is called the modulus of u sub I. So given any complex number that can be expressed of the form a plus bi, we know that the modulus of that element z is z times its conjugate. And it turns out that when you work out all of the complex arithmetic here, you just get a squared plus b squared. Okay, so the modulus of any element is always the square of the real part plus the square of the imaginary part. So a quick example, having a look at the norm of this vector u, we know that the norm of u is the square root of the sum of those moduluses squared. So in this particular example, it turns out that what you get is the square root of the sum of 9 plus 4 plus 1 plus 36 plus 4 plus 16 plus, this should say 4 plus 1. And in this case, it turns out that what you get is exactly the square root of 75. Okay, this same computation applies to vectors whose elements are all real. And in the case where the vectors are all real, it turns out that the norm of the vector is sort of the standard Euclidean length that we expect it to be. So I'll let you work this out, but on this particular example, it turns out that the norm of W is 9 plus 1 plus 4 plus 16 plus 9, all square rooted. And in this case, what you get is the square root of 37. Nope, what you get is the square root of 39 as I've written here. Good job. Okay. So here's the theorem. If u is a complex number, it turns out that the norm of u squared is exactly the inner product of u with itself. And I won't go through the proof of this. It's pretty straightforward. Super useful fact though. So oftentimes in order to compute the u, the first thing we do is compute the inner product of u with itself, and then we go ahead and take the square root. Another useful fact about norms is that the norm has this property of being positive definite. Okay, we've defined the norm or the inner product of a vector with itself to be from the complex field, and it turns out that number is a real number whose value is non-negative. And it turns out that the only way you can get a zero value out of the inner product of a vector with itself is if u itself is the zero vector. Okay, so this ends up being super, super useful later. We'll see this later, but for now, let's just go through the proof. So it turns out that the inner product of a vector with itself is 0 if and only if, by definition, the sum of those modulus squared is 0. Now this can only be true, as it turns out, if each individual element of the vector u is 0. Now if each element squared is 0, then each element has to be 0, and if each element is 0, then u is a 0 vector. Okay, so again here, the take-home message is that a norm is non-negative, and the only way that a norm is 0 is when the vector itself is 0. Okay, so again, this ends up being like super important in projections and things like that, but for the time being, we'll just notice that that a norm is positive definite. Okay, let's talk about orthogonality. Two vectors are orthogonal if their inner product is 0. Okay, so this is a way to define orthogonality in the complex field too. So here's an example. U and V turn out to be orthogonal, and I'll just ask you to verify that. But what you do is have a look at the inner product And by inner product, we mean exactly what we said we meant before, right? The sum of the conjugate of the first element with the first element of V, and so on through the fourth element, and you'll work this out and see that you get 0. Okay, real vectors can be orthogonal too. In this case, we see that x and w are orthogonal, and this is a pretty quick calculation because x and w don't involve complex numbers. So it's pretty quick in this case to see that that x and w are orthogonal. Once we've defined orthogonal, we can talk about an orthogonal set. A set is said to be orthogonal if every distinct pair in the set is orthogonal. Okay, so there's a quick way to write that. And the quick way to write that is that the inner product of u sub j with u sub k is 0 whenever k is not equal to j. Okay, so you know about orthogonal sets. You've probably seen the vectors I, j, k before. Here, we think about the analogy of I, j, k over the vector space Cm. So the jth such vector has a 1 in the j spot and 0 everywhere else. And it turns out that the set of those vectors, again, where the ith such vector has a 1 in the ith spot and a 0 elsewhere, turns out to be an orthogonal set of vectors, right? This is the standard unit vectors from Cm. Okay, in order to see that, it's pretty straightforward. You just go ahead and look at those inner products. And when you write out the definition of Ej and Ek, right, they're only non-zero where I is equal to j and where I is equal to k. And in those cases, you only get one of them being non-zero. Right, so here's where the first one is non-zero, the jth unit vector. And here's where the second one is non-zero, the kth unit vector, and they're not non-zero in the same place. They're non-zero in different places, so we see that the inner product is 0. Okay, other sets of vectors are orthogonal also. Here's a complex set of vectors that's orthogonal. This is messy. So in order to see that this set is orthogonal, again, we have to see that the inner product of each distinct pair is 0, right? So I'll let you verify this, but the inner product of u1 with u2 is 0. The inner product of u1 with u3 is 0. And the inner product of u1 with u4 is 0. Now we're not done yet because the inner product of u2 with u3 is 0, the inner product of u2 with u4 is 0, and then the inner product of u3 with u4 is 0. Now, of course, inner product is commutative with respect to complex conjugation, but the complex conjugate of 0 is 0, so this also shows that, for instance, u1 with u2 inner product is 0. Okay, so as it turns out, this is an orthogonal set. Here's another example of an orthogonal set. The set S containing real vectors is orthogonal. Okay, now I won't go through the verification here, but again, the method is to have a look at the inner product u1 with u2, u1 with u3, u1 with u4, then similarly check u2 with u3 and u2 with u4, and then finally have a look at u3 with u4. And when all of those different inner products are 0, we see that the set is orthogonal. Okay, a really, really, really cool and important feature of an orthogonal set is that it's automatically linearly independent. Okay, so here's how we see that. Let's go ahead and think about an orthogonal set of vectors. And in order to think about linear independence of that set, we'll consider a relation of linear dependence on that set. Okay, so here's a relation of linear dependence on that set S. Alpha 1 u1 all the way out to alpha n un is equal to 0. Now we know that if only the trivial relation of linear dependence exists, then the set is linearly independent. So in order to see that that's true, let's go ahead and have a look at the inner product of this vector 0 with any element of u, say any element of S, say uk. Okay, so it turns out by properties of the inner product that the inner product of uk with 0 is 0, and that the inner product of uk with 0 is the inner product of uk with this 0 linear combination. Now, of course, we know that the inner product is distributive over a sum, so we get the inner product of uk with alpha 1 u1 all the way out to alpha n un. And we also know that we can pick off those constants, so we end up with the alpha 1 inner product uk with u1 all the way out to alpha n inner product of uk with un. Now, as it turns out, because the set itself is orthogonal, only one of these inner products matters, and that's a one where we're looking at the inner product of uk with itself. Now, we know that the norm is positive definite, so the inner product of uk with itself is greater than or equal to 0, and in this case we've assumed that all of our vectors are not 0, so that this is actually greater than 0, so it must be then that alpha k is 0. And if alpha k is 0, you could do this for all these k's, and all of the alpha k's are 0, and that, as it turns out, is a trivial relation of linear dependence. Okay, so the only relation of linear dependence is trivial. Any orthogonal set of non-zero vectors is always linearly independent. This is really, 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 really important and useful, as we'll see later. Okay, the last thing to talk about is a process called the Gram-Schmidt process. I'll state the theorem first and then show how it's used. The Gram-Schmidt process says that if you have any linearly independent set, here our linearly independent set is S, then defining vectors in a new set called T, our vectors in the set T are these U's, and they're defined in terms of V's and the old U's, then T is orthogonal and the span of T is the same as the span of S. Okay, so I won't go through the proof of this theorem, it's in the textbook, but the take-home message is that when S is a linearly independent set, of course not every linearly independent set is orthogonal, but the Gram-Schmidt process gives us an orthogonal set and the span is the same. Okay, so it's sort of an improvement on this linearly independent set to an orthogonal set. So let's go ahead and put this to work. Here's an example of a set. It turns out that this set is linearly independent but not orthogonal. I'll go ahead and let you work that out. But we'll go ahead and use the Gram-Schmidt process to cook up an orthogonal set. So the first thing we do is we set U1 equal to V1. Then we set U2 equal to V2 minus a scalar multiple of U1. Now, in this example, it turns out that U1 and V2 are already orthogonal. So in this example, it turns out that this element is 0, and we get that U2 is V2. And then we do the same thing for U3, sort of thinking about it as V3 minus a couple scalar multiples of U1 and U2. So what we end up with is U1 equal to 2, 1, 2, minus 1. We end up with U2 equal to 1, minus 2, 1, 2. And then I'll let you go ahead and verify this. We end up with U3 equal to minus 1/2, 0, 1/2, 0. Now, however, what we typically do is rescale. Orthogonal sets are still orthogonal if we scale by a constant multiple in order to get rid of those fractions. So we'll take U3 equal to the vector. That vector is minus 1, 0, 1, 0. So I'll let you go ahead and verify that these three vectors are now orthogonal. And again, because of the theorem, it turns out that they have the same span. Okay, now we should sort of be able to see that intuitively when we think about the definitions of U1, U2, and U3. U1 is defined as V1. U2 is a linear combination of V2 and U1. So it's a linear combination of V2 and V1. And V3 similarly tells us that U3 is a linear combination of V1, V2, and V3. So the linear combinations end up translating from the span of T to the span of S. Okay, the last thing to talk about is an orthonormal set. An orthonormal set is a set that's already orthogonal, such that each vector has norm 1. Okay, so we can always cook up an orthonormal set from an orthogonal set. If our set S here is an orthogonal set, and we define a new set called that set S hat as the set of vectors U1 hat out to UN hat, and each hat vector is defined to be the vector from the set divided by its norm, then it turns out that S is orthonormal. Okay, so this set S hat is orthonormal. As a remark, when UK hat is a vector that looks like the norm, UK over the norm of UK, then UK hat is called a unit vector that's parallel to UK. Okay, so basically an orthonormal set is an orthogonal set where each vector in that set is normalized. So just a quick example. Here's a set that we know is orthogonal. This set is obviously not orthonormal because none of the vectors have norm 1, but we can pretty quickly compute U1 hat, U2 hat, and U3 hat, dividing U1, U2, and U3 by their norms. That new set will be orthonormal. So we quickly see that the norm of U1 is the square root of 10, the norm of U2 is the square root of 10, and the norm of U3 turns out to be the square root of 2. So when U1 hat is 1 over the square root 10 U1, U2 hat is 1 over the square root 10 U2, U3 hat is 1 over the square root of 2 U3, then U1, U2, and U3 hats form an orthogonal set that's has norm 1, so it's orthonormal. Okay, orthonormal sets are even better than orthogonal sets, as it turns out. Sometimes they're not worth the bother, but they are really, really important. So you should know how to form an orthonormal set from an orthogonal set. Okay, folks, that's it for orthogonality. Hope you've enjoyed this video. There's a lot of information here, but a lot of it is familiar, and what is not familiar should be pretty straightforward. Have a great day, and we'll see you next time. Bye-bye.